2015 question number 3 starts by giving us a table of values for t and t being in minutes, and v of t, your velocity, or Jonah's velocity in this case, because Jonah is jogging. Nevertheless, going to part A, using the data to estimate the value of v prime of 16. Well, we look here, right? T, we're going to look for t of 16. It's not here, but we know it's between 12 and 20. So we're going to use an average slope to estimate v of t. Now, anytime you use an average slope or your basic algebra 1 slope, you're going to get an average derivative. And here's what I mean. So using the points they give me, right, the points that they limit me to, using my algebra 1 slope is simply my change in y over my change in x. So if I'm using 12 and 20, because that's where 16 is between, then 20 minus 12 on the bottom, and then 240 minus 200 on top. I simplify a little bit, and I get 5 meters per minute squared. Now this tells me, this algebra 1 slope tells me my average acceleration, right? Because here I took values of velocity, and because of the slope of velocity, the slope is sitting as a derivative, so this is going to give me average acceleration. And this question is worth 1 point, and it's just for the answer. There's not much to set up and show, so it's either 1 point yes or no. Part B is a little more conceptual. We have to explain the meaning of this integral, not just the integral of velocity, but the integral of the absolute value of velocity. And so what does that exactly mean? Well, we know velocity can be negative and positive, and it's simply telling us the rate at which we're traveling, the rate at which we're moving from a fixed position. If I start here, I'm going 16 miles per hour, maybe north, and then 20 miles per hour south. But if I take the absolute value of that, then that's going to give me overall distance traveled. So it doesn't matter if I went 5 miles north and 5 miles south, and I end up at the same spot, my overall distance traveled is 10 miles because I went 5 up and 5 down. Essentially, distance cannot be negative, so you put an absolute value, and this gives you the overall distance traveled. So in the case of this question, you can simply say the integral of the absolute value of velocity. Remember, the absolute value that's important is going to be the total distance Jonah jogs in meters between 0 to 40 minutes, or in the first 40 minutes. But really, these absolute values make a difference. If there was not an absolute value, then it would simply help explain where the new position was. So if I ran 5 miles north and 5 miles back south, distance traveled, the absolute value would be 10 miles, but my position, right, without the absolute values would be 0. Now, that's not all they're asking for. Part B is also asking for us to estimate a right Riemann sum with four subintervals. Now, using Riemann sums and tables, I always remember as this: if it's a right Riemann sum, I start at the right and I go left. If it's a left Riemann sum, I start on the left and then go right. So what is this going to look like? Anytime you do a Riemann sum, you're going to leave off one of these values. It's either the leftmost or the rightmost. Now, if I'm starting at the right for a right Riemann sum, that means I'm going to leave off the 0. I'm going to find this change in my x, or in this case my t, change in the t variable times this one value. Change over here, this value. Change here, here, change here, and finally keep this value. So here's what it will look like. When I integrate using a Riemann sum, right, distance between, or change between 24 and 40 is going to be 16, and I keep the 150 value. Now remember, we're doing the absolute value of velocity. So, and this is where a lot of students are going to mess up. They're going to have the correct interval for the t, right? Change from 20 to 24 is 4, but they're going to make the mistake because they forget its absolute value. They're going to put negative 220. But you have to make sure, if you're finding total distance traveled, distance cannot be negative. It's always, you're adding distance every time. You cannot undo walking 5 miles. So in this case, it would be positive 220. And the cycle continues again, as you can see here. Again, you can get the answer, but the answer is only worth 1 point. Most of your points come from the explanation from top and the setup of the Riemann sum. So even though this is a non-calculator section, you can still get a point for the setup and then maybe miss a point for the answer because you weren't as well with multiplying or adding. Final part, part C. Now this is important. Wait, no, hang on, not the final part, but next one will come up. Part C is simply asking, not yet, finding the acceleration at t of 5, given that b of t is equal to this weird equation we don't care about. Now the thing to remember is that it tells us that b of t is Bob's velocity, right? It's not Bob's position, it's Bob's velocity. You'll see why that matters here. Right, here's a simple relationship between position, velocity, and acceleration. Velocity is a derivative of position, and acceleration is a derivative of velocity. So if we place b of t here, because we are told, right, in part C, that b of t is Bob's velocity, b of t is going to go here. This tells me that to get to acceleration, I'm going to have derive once. Whereas if this was Bob's position instead, b would be over here. I'd have to derive 2 times to get to my acceleration. So doing a basic power rule, I find that b prime, not b double prime, is 3t squared minus t, and I simply plug in t is equal to 5, and I get 15 meters per minute squared because it's it's acceleration. Again, 2 points, 1 point for the actual answer, but the point comes in from knowing it's b prime, not b double prime, because again, the relationship here explains why you take the first derivative, not the second derivative. Finally, part C. Now this is the part to really pay attention to. In part A, we want to estimate a derivative, right, by taking the average slope. In part B, we're going to take the average velocity, or in this case, the average value. If we're given velocity here, we want the average height of the graph in some sense. And here's what I mean between these two values. Right? Anytime I do an algebra 1 slope, I'm going to find the average derivative of f prime. So this is going to give me an f prime out. Whereas if I use this equation, right, that we've all seen before, the average value, it's going to give me the average height of the graph. If I were to quickly sketch it out here, we have a nice flowy graph here. Algebra 1 slope would be from here to here. Whereas my average value would be right over here, the average height of the graph. So that's important. We want to find in part C the average velocity. So if we do an algebra 1 slope, we'll get an acceleration at the end. We don't want acceleration, we want velocity. So we're going to stick with this bottom formula here. Just by knowing that and being able to apply that, you're going to get the point later on, and you'll see that. So my overall setup here, they want us to use the equation in part C. And here's my overall setup, just again following the basic formulas from 0 to 10, 1/10. Integrate with the basic power rule. You may mess up here and there because it's not a calculator question, but don't stress because the answer is only 1 point. You get most of your points from the setup and the extra point from doing the antiderivative properly.